like to talk about the main actions for average. So maybe as a background in general relativity, you have the Einstein equation. My stress tensor is theta. We're going to use T for some other things. And of course, if you have any metric, any random metric, you can of course compute Einstein tensor and then define the stress energy tensor to be just that. And you have a solution. It's of course not a very meaningful solution. So the real thing you should be doing is to write down the stress energy tensor and then solve for the metric, or rather you write down the stress energy tensor and you solve for the matter fields and the metric. But oftentimes in general relativity, you if you want to understand things about the space-time metric or a metric solving this equation, you're not really in every case need the complete details of this object, but you are okay with certain general conditions. And one such conditions are energy conditions. So there's the null energy condition, dominant energy condition, various other things from energy condition. So I'm not reviewing them here, but the null energy condition is just that it's supposed to be not negative for any null connected in. And why is that an interesting condition? Why is that? Why do you? So you know that the Einstein tensor is literally minus a half this piece. So if you contract this twice with a null vector, this piece does not make a contribution. So v mu therefore is related to this by the Einstein equation. Same as R mu. And by this condition, you therefore find that the Ricci tensor dotted twice into the null vector has a sign. And now, why is that interesting? There is an equation called the Ricci equation. So it's just the name for the null component of the Einstein equation, nothing more. So if you have some components left in the Einstein equation, you can just take them and give them your name if you do something with them. It's just a component of the Einstein equation. But the Ricci equation, if you take an affine parameter, lambda, so it says that the expansion is minus this is another theta, the little theta. This is the expansion of the null converse tangent to mu, and this is shear, and the shear squared numbers in front which are and your conventions for defining the shear and the expansion rate. Be careful about this, and this is your rigid term, and lambda is an affine parameter along the congruence. The picture is something like this. So you have some congruence if you set up tangent to k mu suitably. So these are all supposed to be parallel here initially. Maybe I should also draw them like that. Set them up parallel, that means congruence. And then they pass through some curved geometry, and they will do various things. So you can compute the area of such a cross section, and then later, and how this area changes is the expansion. So infinitesimal change. Everything is infinitesimal, and this is supposed to be infinitesimally small area. Lambda is mu, and lambda is along the area, rate of change of the area. So, as you know, in general relativity, then the geodesic corresponds to a freely falling observer or freely falling object. These are null geodesics, and so they don't feel any acceleration. And so if the expansion is positive, then they diverge from each other. So, and the expansion is negative, they converge. So this is related to focusing or defocusing effects. So this equation is nice because all terms here have one sign if the energy condition is fulfilled. So negative. So this for starters not a sign of the expansion but of the derivative of the expansion. And so this means that the derivative of the expansion has a sign. So if something, let's say, contracts, it will contract more and more. That's what this says. It doesn't say something immediately about the sign, but about the derivative of this. So it's used in the singularity theorems for this reason. Because you can learn focusing effects. So this is basically the one reason why it's interesting to just, it's relevant to just know about some certain sign of the stress energy tensor. So my colleague Dan in Leipzig once said that in these theorems you shouldn't think of the Einstein equation, but you should think of it as the Einstein inequality. Because really what you're using is just a sign of some things and not really an equation. I think that's the right way to think about it. It's the Einstein inequality. Of course, in a real model, you have a microscopic. Usually, you have a microscopic model for the matter field. So, I mentioned this Van Gordon field, phi, and then the stress tensor would be something like that. formula for the Gordon field, and it's easy to see that in this case you got that twice. This is a matrix, so if you contract it into a null vector, it doesn't contribute anything. So you're only going to get a contribution from this term, which you can write as a perfect square. So in this theory, obviously, since a perfect square can be negative, you have the null energy. So you can do the same exercise for the Maxwell field, the engaged field.
May I ask you, if you have an expanding universe, what's the meaning? That it will expand less and less?
More and more.
More and more?
Yeah. So what you usually then think of it in the past, so it will contract more and more. So it gives you, so there are different statements, then there's sort of, you can use it to derive a cosmological Planck type singularity or geodesical incompleteness. This is by itself not the only ingredient in the proof. This is just a local ingredient. Of course, you can, even in flat space, you can have completely harmless things, something like a caustic, where you have some geodesics. Now here they are initially expanding, but so they can do something like this. They can enter the light cones of a caustic if you have a beer glass or something, and you can see these bright spots. And that's what we here. And so in here also this expansion would become infinite. But there is nothing singular about this point. It's just a caustic. And so this is usually combined then with some global information where you apply this to a globally defined null sheet, like the past of the boundary of the past of future infinity, where you know that such kind of things for global reasons cannot occur. And so if they do occur, somehow it must therefore be related to some pathological. So this cannot occur if you have a nice space-time. And so if they do occur, this must be related to some actual singularity. So it's the combination. And also in the cosmological setting, you have some global part. The local part is, I think, was already understood long before Dr. Penrose and others. But it's this global part. Okay, so now we're in curve T. The back does not hold simply. And why? So it's basically because of quantum mechanical interference. And I have this example in my lecture notes, which I took from a paper by.
Excuse me, Stephen.
Yes.
Curiosity. In Euclidean space-time, the neck is unused.
Yeah, then it's some condition on the Ricci positivity of the Ricci tensor. So that it means just that the Ricci, there are no null vectors, of course. It means that the Ricci is a positive definite quadratic form.
Okay.
So it also has consequences.
Right.
Riemann geometers have many theorems, like what happens if the Ricci tensor, if you have certain conditions on the eigenvalues of the Ricci tensor, and what that means for the geometry. Many.
Okay. So it's equivalent one. In general, all the energy conditions can be reformulated in the Euclidean?
No, it's really a Lorentzian thing, though I'm just meant to say that you can also, and people do impose some various conditions on the Ricci tensor, like all eigenvalues positive, all eigenvalues negative, or some eigenvalues always dominated by others. There are tons of theorems, but the consequence are different things usually. for instance, if the eigenvalues are all negative, then asymptotically the space is like a S space or things like this. Okay. Now I wanted to tell you why the neck doesn't hold. You can actually prove this, but I like better this example. And as I said, it's not due to a very core. So you can look at the Klein-Gordon field, where this stress tensor, in fact, in Minkowski space. And so the stress tensor would be just the quantum operator, and in Minkowski space, it really just is the normal order operator. So phi, and so you would write your field phi. Field, and then you can formally write down this expression, and you normal order it as you learn your T course to get an operator. Yes. And now you can look, for instance, you can define a two-particle state, a superposition of the vacuum and the two-particle state. Put some wave function here. I'm going to explain some wave function. Two-particle momentum eigenstate, so this is the notation slide. This should be A. And now you can, I'm not going to look at the null energy condition. I'm going to look at even just the energy density, so you can compute just the 0,0 component. You can also compute the null component, but it's slightly more complicated. The 0,0 component also is positive. You can also classically write it as a sum of squares, and because you have the 0,0 squared here, and then if you work out the signs, this is minus a half times the 0 squared, and this is a plus. So this can also be written as a square, and you can compute this based on some concrete answers for this, and I'm taking to give you the intuition where this is really coming from. So they, Ford et al. Make this following ansatz. This is not the only possibility, but it is so I power half, and this chi is a step function in such a way that I have p 0 p not, and 0 is bigger than 2 P naught. And then also say C0 P2 0 P1. So you have make this ansatz. So what does it correspond to physically? So P this means that the wave function, the two-particle wave function, that's what it is peaked where, because of this condition, is peaked roughly when the momenta are opposite. Yeah, so the sum of the momenta is 0. So this means basically P1 is roughly minus P2. So you have two colliding waves basically with opposite momentum. So you write one wave like this, and then the other wave will be sort of slightly tilted. The momentum goes this way and that way. And in this case, because it's a superposition, you're going to get an interference effect from the two waves. And if you do the calculation, this interference effect, let me write a space-time picture. T is x. So let's do something like wave, and the other wave is going to be have the opposite momentum, do something like this. And so you can kind of see that when the waves can constructively or destructively interfere, and you're going to get a pattern if you plot this thing, which has an alternating positive and negative parts. Simple calculation. And furthermore, these patterns will always alternate in any time-like direction. You can do this calculation. I think it's nice if you can just do a mathematical script, a little one, and just plot it. I think that's the most efficient way of doing it. You have these three parameters, nu, chi naught, and the cutoff, which you can still tune. Yeah. And you can also demand that the state is normalized. Pure quantum mechanics. And so you see that you in particular have pieces where this is negative, but because it's an interference, it must always alternate with something where it's positive. Yeah, that's the idea in quantum mechanics. You get these interference patterns, but they kind of alternate. And so if you may think that therefore while this can be, if you're just in a negative dip, it can be negative. But if you integrate over time, sooner or later it will be followed by a positive dip, and so on. And so you may think that if you integrate over time, the positive dips will eventually win. Mm-hmm. That's the idea behind this averaged null energy to average conditions. And in fact, you can I like this one part because you can just work out everything using really basic formulas. It's tedious. And you can also look at paper. What's done. So the conclusion from this example is that in the energy, in the expected energy density T of x, is varied. X and positive and negative. Values of rho alternate, and even though the negative ones can become arbitrarily negative, you can observe in this example that then they must be followed by an even more positive piece. So if you really want to set this up in a measurement, you have to be quite careful and really find those negative pieces, this kind of negative values with high resolution. So the idea therefore is that maybe if you took some integral of this, t in x, energy density, if you took some integral of this, and maybe you would maybe have here some probability distribution, something function. So the idea is that this may perhaps always be positive. Yeah? So you cannot somehow beat this. So this is still not quite true because you can take the window function so that it sits exactly in the negative pitch. But then you will be in general be punished by having a large derivative of this. So this is not actually true. So the real inequality is that if you put a bound on the derivative of this, so you cannot localize it in just a valley, and then this cannot become too negative. But another way is to just, in a way, keep this just constant and just average. So this cannot be done with this energy density, but it can be done arguably with the null components. So something like if you take kk, do lambda. So k is again my null vector. For example, it could be 1, 0, like, and lambda is the affine parameter. So the NX is the statement that this is supposed to be positive. And the NX, so it avoids this averaging function. But the idea is the same, that so this integrand can have both signs. The positive sign, the positive part will dominate over time. So A is for average because this is average. It's not really an average, it's just the integral. Now, it's not obvious that this is true, though. So in flat space-time, it is true. And so also if mu is tangent
Is this still for Klein Gordon or?
Yeah, this is arguably in total generality, and this also in total generality. Okay, but in general, it's not okay. So if you take an arbitrary, even for Klein Gordon, if you in a curved space-time, you take an arbitrary null congruence. So certainly you can find null congruences where this is not positive. So an example is, of course, this T mu is very difficult to calculate. But if you, for example, what we calculated in recent years a lot, so we calculated something like the stress tensor. We calculated the stress tensor in Kerr space-time. In Kerr space-time has something called an inner horizon. And calculate the stress tensor of the null component of the inner horizon, and it can be infinitely negative even if you integrate it all the way. So it doesn't always hold. Well, the idea that what people believe about that quite far from proof is that the back reaction forces so in other words, if you do just a fixed quantum field theory on a fixed curved space-time, it may not be true, but if somehow the space-time is a semi-classical solution to the Einstein equation, meaning that the mu in some sense is by the expectation value of the state, then it's supposed to be true. So there is no proof of this. People from Wall and Flanagan from the 80s, where they argue, or they give evidence for this, but it is kind of generally. Okay, but in Minkowski space, it's okay. So you could do this, it's instructive actually to do it in this example. This is not a proof of this, because this is supposed to be a general statement for any quantum state or any regular quantum state, and not just a proposition of the zero and the totality state. But for a free field, it's kind of just such an idea. Now, I want to spend a bit of time on this now, because it's related to something called a half-sided modular fusions that originated in algebraic quantum field theory maybe something like 30 years ago. Back to work of Borchers and Wiesloch, people that were active before I even knew what algebraic quantum field theory was. So I'll explain what the half-sided modular inclusion is. It wasn't originally invented, I think. Having this in mind, though I don't honestly know, but I'll explain what it is, and the connection is still a bit heuristic, I would say. The concept of half-sided modular inclusion is totally 100% mathematically precise, but the connection to the NX, I think, is a bit heuristic, but it's without doubt correct. So let me explain what a half-sided modular inclusion is, and maybe how it relates to the NX, and then on to something perhaps even more interesting called the QNX. So since we know about the modular operator, let me first state abstractly what the half-sided modular inclusion is. And so what we have is two Neumann algebras, N and N. Not one, but two. And we have a vector in the Hilbert space on which the von Neumann algebras act, which is cyclic and separating for both and so that's not so then we have as you know we have the modular operator, and the idea is if you so this is the modular operator for M. Well, let me emphasize that it's for M by putting M here. So it of course can act also on N. The idea is that this remains in N for T greater than 0. This is the condition. So the picture that you're invited to consider is where
Okay.
M
So should remain in N. In the big algebra.
It is always in N.
Okay.
M is always
Yeah.
there, but in N,
Yes, yes,
maybe I did. My letter was. So M is the so this the characteristic example is the algebra of a right wedge across the space. And then I can consider a cut here. So let's first consider 1 plus 1d. Let this be some distance t. So and so then I get another wedge. Call this WT. And W is the whole thing. And M is a W, and N is shifted wedge. And as other colleagues explained to you, in this example, we know what is the modular flow of M. It's the boosts. And so obviously, the boosts will move this wedge inside itself for positive times. Of course, for negative times not. But for positive times it will move inside this wedge. So this is therefore an example of this half-sided modular inclusion. Now I'm going to draw a picture with more dimensions, hopefully. Okay, so this is supposed to be so now this is supposed to be a wedge in more dimensions. So there is now an edge of the wedge which has as a codimension of 2. And this reminds the edge of the wedge. And then I'm going to call this direction x plus. And I'm going to call this direction minus. And now my algebra M is still A of the wedge, but I can take advantage of the fact that I'm in higher dimensions, and now comes the difficult part of the drawing, I suppose. You can, so here this apex characterizing this shifted wedge is just a point. But really, in high dimensions, you have more directions going this way. So you can think of this cut, this cross-section, as being characterized by the fact that x plus is some non-trivial function, a positive function of the edge coordinates. In other papers. So then again, you have this other wedge, P, which is again inside. And so this also for any positive function of smooth or whatever is again a half-sided modular conclusion. Set up, and so what's the basic structure theorem? About half-sided modular inclusions. So the point is you have, because of the second condition, you have two modular operators. Namely, you have this one, and you have, for the same vector, you have the modular operator for the other algebra. So you can, for instance, consider this kind of a combination. It's a unitary operator. And it turns out that this unitary operator can be written in a certain way. So it can be written as the exponential of I times 2 pi t minus 1 times some operator I'm going to call E sub t. So in the math papers, this is usually called P. So the point is, the structure theorem is that ET has a positive spectrum, and then it satisfies these kind of relations with the modular operator. So this one, of course, you know what it is. This one is a boost. But this one, if the edge is curved, you do not know what it is. So though you can relate it to something, and if ET, you can consider this for different keys and work out the commutators, at least formally, for different keys, and you realize that the ET and the omega together, also the operators E to the I and ET, and the operator M, they generate a representation of the so-called, or part of the so-called BMS group. I'm not going to explain what the BMS group is, but I'm going to explain in this example. So in this example, in this 2D example, T is just the word. So here T is just a number. So T is T times the P, I guess, here, P plus component of the energy momentum operator. So P is the energy momentum operator, which in 2 dimensions, of course, gives, I guess, minus the Hamiltonian Hamiltonian in the momentum. So P plus is the Hamiltonian plus, is the plus component. X plus is this component. And so in this case, this is either this is a null translation. And this
Some
is
parameter S.
here.
Yeah.
I already have t, so in a way I already have.
Okay.
Yeah, but I could put. Okay, so for a fixed t, yeah, you're right. So if I consider t as fixed, then I have two parameters a and t, group t, and the group that's generated by just this for a fixed t is just the affine group in one dimension. So the ax plus b group, yeah, affine transformation. And so that's kind of expressed as a relationship. But sort of heuristically, the point is that you can think of ET because of these relations with the EMS group. You're invited to think of this as the following. It's the stress energy tensor, the plus component of x plus, x minus 0, and then a, and then d to z. It's a null component stress tensor integrated over this along this sheet example. So the motivation why you say it is because of the commutation relations that these things have, and you say that formally they have the same commutation relations as this work object would have, and therefore you say they're the same. Yeah? But this is not the first part of the proof. That's rigorous, but this, and I also put it in quotation mark, is not rigorous because, for example, the notion of half-sided modular inclusion nowhere even mentions the stress energy transfer. So you could think of a quantum field theory which just doesn't have one. There are such theories. And so it's under additional assumption somehow that there is a stress tensor. So the average null energy condition basically follows. So because you know that the expectation value is positive, that's nothing but this condition. And then you not only that, but you know it's positive for every positive function t. So if you imagine you put t equal to a delta function, which is positive, and then you pick out the value of theta plus plus integrated over x plus at a fixed value of z. It can be the integral over 1 now. So the nx follows 1. I'm taking t of za to be a delta function. So this is the proof of the neck. I said again, there is no rigorous theorem. The connection with the stress energy tensor is not totally watertight, and I think that last part would still benefit from some rigorous work. moral proof. Okay. Now you can also write down a formula for the modular operator with a smaller wedge. So again, you can kind of say maybe this. You could maybe write it in terms of formal density matrix. So then if you take the trace over the complement of this wedge, if I have color, might look quite so messy. So you can look at the complement of the wedge, which would be kind of this thing. And you can take the complement, look at the reduced density matrix of this shifted wedge, which is what you get when you trace out over the complement, and then this is supposed to be equal to KT is a similar expression. So here you take x plus minus So in a sense, you have also a formula for the modular operator in terms of the stress test. Okay, so this is not quite honest business because actually this you should really draw this in the space-time in a Penrose diagram to see this would also have a contribution from future null infinity and from time like future infinity, and from this one. So this is what I wanted to say about the ANAC. I think it's very pretty. What it is. I think from a rigorous mathematical viewpoint, it would be satisfactory to make this connection between the stress tensor and the generator that you get from the half-sided modular and is more precise. You would have to make certain assumptions, but that mine has not really been done. Okay, so there are any questions about the ANAC?
Should we take a break now?
Yeah, maybe.
Any question?
They can